So far, you have seen an example related to direction field and solution curves of differential equations. Now, for definitions of direction field, so the definitions of direction field is presented right here. So it's longer definitions, but the idea of this is that direction field suggests the shape of a family of solution curve of the differential equations that you're working with. My example in the graph on the website that if you have a differential equation and you plot the differential equation, you can see a bunch of arrows that kind of indicate the directions on which the solutions will move. Right? And if you click anywhere on the grid, then you can see that you can visualize the solution curve corresponding to those direction fields. So that's the definition of direction field. Now I'm going to move on to another concept called autonomous first order differential equations. You can have autonomous system of differential equation. It's more fun to work with, but is not the topic that we would like to cover at this point. But later in the course, when we have a chance to look at the system of differential equations, then autonomous system of differential equation is something that we could like to explore. But for now, you want to look at autonomous first order differential equations. Right. So what is the definitions of autonomous first order differential equations? So an order differential equation in which the independent variable does not appear explicitly is said to be autonomous. Right? And the differential equation is written in this form. So you have dy dx equal to f of y. In this case, x is the independent variable and y is the dependent variable. For example, you have a differential equation of the form dy dx equal to 1 plus y squared. Right? On the right-hand side is the function in terms of the dependent variable only. Therefore, this equation is called the autonomous differential equations. In another cases, you have dy dx equal to 0.2 times x times y. So the right-hand side of this differential equation is the function in terms of both x and y, or in terms of both dependent variables and independent variable. Therefore, this equation right here is called non-autonomous differential equations. Now, I want to relate this concept to a population dynamic example. Right, so you have, for instance, the differential equations dp dt equal to r times p. So this differential equations is an exponential growth model, assuming that r is a positive number or a positive constant. So the idea of autonomous differential equation in the context of exponential growth model is that the growth rate at any moment depends only on how much you have right now, not on what day or what hour it is. Right. So what I mean is that let's say is 9 in the morning or 3 in the afternoon. If you have, let's say, 100 bacteria, they will multiply at the same proportional rates as R. Right. So the exponential growth is autonomous because time itself does not enter the formula. I hope that makes sense to you. It's only the current stage that we're looking at. In other words, the population change just depends on the rate, on the growth rates R, and the growth rate R does not depend on time whatsoever. Right? So that's the example of autonomous first order differential equations. Now we're going to move on to another concept. So the concept of critical points you have seen before already, right? When you take calculus 1. To find critical points, you take the derivative of the function, set that equal to 0, and solve for the value of x. That's what you did to find critical points. We're going to have a similar definition for critical points in the context of differential equation. Just that for autonomous differential equation written in this form, dy dx equal to f of y. To find critical point, you just set the equation equal to 0, f of y equal to 0, or dy dx equal to 0, and you're going to solve for whatever value that you need to solve, right? So whatever you find, you have the critical points. There's another name for critical point. It's called equilibrium point or stationary point. And all of these 3 points or terminology are used interchangeably. So you can say it as critical point, or you can say equilibrium point or stationary points. Now, equilibrium solutions. The definitions here is that if C is the critical point of the autonomous differential equations, then y of x equal to C are the constant solutions of the autonomous differential equation. And the constant solutions of the autonomous differential equation is called the equilibrium solutions. And all of this concept, critical point, equilibrium solutions, and autonomous differential equation will lead us to something called another qualitative technique called phase line. Okay, we're gonna draw the phase line for exponential growth model. We're gonna and logistic growth model, and another one here is the logistic growth with the threshold model. So plot the phase line to exponential growth model. So first of all, what you have the autonomous differential equation. So that's a given. You need to find critical point, and then from critical point, you can say that you have a equilibrium, a constant solution, or equilibrium solutions. And to find the critical point, what you do is very straightforward. Just set the right-hand side equal to 0. So R times P equal to 0. R is the growth rates, P is the populations. So there is only one critical point or one equilibrium point or one stationary point. That is P equal to 0. Now you're going to draw a phase line. That is, draw a vertical line like this. And this is, we call that the P-axis because of what we have for P. Right? We don't care about time. There's no time component here. And there is only one critical point or equilibrium solutions. That is P equal to 0. Now, below, we have things going on below 0 when P is negative. You have things above 0 when P is positive. But in the context of populations, you don't want to consider a negative value. But we get to that later. Now, how would you know the behavior of the solutions without noting the exact value of the solutions, right? We haven't learned how to solve this differential equation at all, but do you know the behavior of the solution? Okay, so you have P equal to 0 is the equilibrium solutions. Now what you do is that you're going to try a few different values for P to see how dp dt behave. Okay, very similar to the case of direction field. Is the derivative less than 0? Is the derivative greater than 0? Or the derivative is equal to 0? In the case of derivative equal to 0, you have the equilibrium solutions already. Okay. But in the case of P is positive, if P is positive, what you do is that dp dt equal to R times P is also positive, right? Because the growth rate is positive, right? P in this case also positive, and therefore you can draw an arrow pointing upward, right? Because P is always positive, so the PBT is always positive. So again, in the context of population, you shouldn't consider a negative value, but for the sake of the analysis, what I'm going to do is just going to consider a negative value as well. So in the case of P is less than 0, you have dp dt equal to R times P. So R is positive, P in this case negative, and therefore the product will give you a negative value. And therefore, this is the arrow pointed downward. It's negative. That's how you analyze the solutions of P using the phase line. Now, this is called the exponential growth model. Therefore, you see that the solutions of this particular equation is going to be an exponential function. Good. And the exponential functions you learn in pre-calculus or college algebra is the increasing functions. Okay. So if you incorporate, right, just the case where you incorporate the value of t, and you will want to draw the exponential functions. So this part is going up. Right? So exponential function is an increasing functions. I illustrate this particular point. So that is for exponential growth model. Now for logistic growth model, the first thing you need to do is find critical point or equilibrium solution. Then you're going to draw the phase line into the similar analysis. So this is autonomous differential equations because there's no explicit value of t on the right-hand side. You set this equal to 0, and you're going to have two solutions. Rp times 1 over p, 1 minus p over k equal to 0, indicate that you have p equal to 0, and you have another case where 1 minus p over k equal to 0, or p equal to k for that matter. So there are two critical points or two equilibrium solutions. I'm going to plot this. the p-axis. P-axis because the value of p, the values are, that's the value that we're looking for. Right, so there are two equilibrium points, p equal to 0 and p equal to k. We want to analyze the sign of dp dt. Right? You want to know if it's less than 0 or greater than 0. So there are three regions that you need to consider. The regions where p is greater than k, the region between 0 and k, and the regions below 0. Again, in reality, we don't consider a negative value for population, but for the sake of the analysis, we're going to consider all three intervals. So when p is greater than k, let's say you substitute in 2k, right? You just choose any value, right? That is greater than k. For example, p is equal to 2k, you can do 3k, 5k, whatever. But what you have, let's say p equal to 2k, you do the analysis, you have dp dt equal to r times 2k times 1 minus 2k over k. Okay, so the k cancel out, and you get 2r times k times 1 minus 2. That's going to be less than 0. Okay, and because of this less than 0, you draw the arrow pointing downward like this. Right? Initially, if the population is around here, it will eventually have to approach the carrying capacity k. Now for the second interval from 0 to k. So when p is between 0 and k, what do you have? You can choose p to be k over 2. You do dp dt equal to r times k over 2, because again p is equal to k over 2, times 1 minus k over 2 altogether over k. And this gives you 1/2 r times k times 1 minus 1/2. Again, I don't care about the exact value, I just care about the sign of dp dt. So in this case, the sign is going to be positive. Okay. So this positive indicate that the arrow pointing this way. That is say that if the population, the initial of the population fall within this interval, the population will reach the carrying capacity. Again, in reality, we don't consider a negative value for the population, but for the analysis, let's just do it. When p is less than 0, you have p equal to, let's say, negative k, whatever that is. Negative k, so dp dt equal to r times negative k times 1 minus negative k over k. This gives me negative rk times 1 plus 1. So this is negative. So the arrow to point downward. We good? That's how you analyze it. So this is the phase line. 0 and k are equilibrium points or solutions. The arrows indicate how the solution is going to behave. And you're going to see this in the next lecture as well, when you're going to analytically solve for the solutions of logistic growth model. But in the meantime, if you incorporate the t-axis as well, so this is the carrying capacity, this is the 0 value, the solution is going to look like this. It's increasing, the solution decreasing this way, the solution decreasing this way. Okay, so I don't know the solution curve exactly, but from the phase line analysis, it's allowing me to draw out the solution or to sketch out the solutions. Okay. I know that if I start from this area, the solution is going to increase. If we're going to start out with the initial value of population somewhere up here, the solution will dip down to and approach the carrying capacity. Okay, so that's it for logistic growth model. Now, the baseline analysis, direction field solution curve are extremely important for differential equations that cannot be solved analytically. One of the differential equation of that problem is this one, logistic growth with the threshold model. At this point, there's no way that you can solve this solutions analytically, so we can just use phase line analysis to solve the solution or to observe the solution curves. We're gonna do the same analysis that we did in the last two example. All right, so this is again the autonomous differential equation because there's no explicit value of the independent value time t. To find a critical point or equilibrium point, you set this equal to 0, and you get three values. P equal to 0. 1 minus p over k equal to 0 implies that p is equal to k. And p over t minus 1 equal to 0 indicates that p is equal to t. For p is the populations, k is the carrying capacity, and t is the threshold. All right. Now you draw a phase line. This is the p-axis. You have three equilibrium point or three equilibrium solutions. One is 0, another one is t, and another one is k. Now, when you do the analysis on the BDT, there are 4 intervals that you need to consider. The interval that is p greater than k, the interval between t and k, the interval between 0 and t, and the interval less than 0. So in the case of p greater than k, so choose p equal to 2k. So dp dt equal to r times 2k times 1 minus 2k over k times 2k over t minus 1. So this part is positive, obviously. K cancel out, give you 1 minus 2, so that part is negative. K is greater than t, and therefore 2k is definitely greater than t, so this is greater than 1, minus 1 is still positive. Therefore, positive times negative become negative, times the knob to positive become negative. So this is negative value. And because it's negative, dp dt negative, so if you start out somewhere up here, the solution will dip down to the carrying capacity. Now, when you consider the case where p is between t and k, you can choose any value of p. I'm going to choose p between k plus t divided by 2 halfway points. Okay, then just substitute in here and do the analysis. It's going to be r times 2 times k plus t divided by 2 times 1 minus k plus t over 2k times k plus t over t to t minus 1. If you calculate, just going to avoid this, it's the bad choice, but it has to be a positive number to indicate that the arrow is going to point up within this interval. You're going to carry out the same analysis for the case between 0 and t. So case between 0 and t, and you will see that the PDT is less than 0. So indicate that this is the arrow. And then in the case of p is less than 0, so we're going to have the PDT to be positive, indicate that the arrow is pointing up. Again, in the case of in the context of population, you don't consider a negative value, but it's there for you to consider if you want to theoretically. All right, so if you incorporate time axis in this analysis as well, you can draw out the solutions curve without knowing the exact value of the solutions. That is, if you have the population starting above the carrying capacity, the solution curve going to dip down like this and approach the carrying capacity because it's a decreasing function. If the solution between the threshold and the carrying capacity, the solution is going to behave like this. Okay. If the population start out below the threshold, it's going to eventually approach 0 and die out from the population. Okay. So that's how you analyze the autonomous differential equation. In this case, the first order autonomous differential equations. Autonomous means that there's no explicit value of the independent variable present in on the right hand side of the equations. There's another information I want to relate to you, that is you have attractor and repeller. Right? There's only three. I explained the fourth later, but there's only three attractors and repellers that you need to care. And this is kind of classifying the equilibrium points that we have. So in this case, you have the equilibrium points where all the arrows kind of pointing into that particular points. If you consider this equilibrium point, you see that the arrow pointing away from that equilibrium points. Okay. So suppose that y back is a non-constant solutions of autonomous differential equation dy dx equal to f of y, and c is the critical point of the differential equation. There are basically three types of behavior that y back can exhibit near c. So you see the plot here, see the critical point, y of 0 is just the initial conditions. You have, for this case, the critical point C, the arrows pointing toward critical points. So that is the attractor. Right? So that critical point attract all the arrows. And when you have an attractor, you can classify the attractor as asymptotically stable. Okay. So what is asymptotically stable? The solutions, curves, tend to converge to a specific point. So whatever you have here, the solutions will approach the critical point or the attractor, so you can classify that critical point as asymptotically stable. Asymptotically is that in the sense that you want to look at the behavior of the solutions in a long time as t equal to infinity. Now, in the case where you have a critical point and all the arrows pointing away from the point, is called the repeller. When you have the repeller, you can classify the point as unstable equilibrium point. So unstable, that means the solution curves diverge away from a specific point. Okay. Now I say there are just three times. What about the full picture? So the last two can be clumped together and called a semi-stable. It's neither an attractor nor a repeller, really. It's just that when you consider the critical point, on one side the arrow going toward the critical point, on the other side it's going out of the critical points. Okay. So in that case, you say that it's semi-stable. So solutions converge on one side and diverge on the other side. Okay. Very, very powerful tool. So that's it for me for today's lecture. So in this case, for this lecture, sorry. In this lecture, you talk about direction field and solution curve to the first order differential equation. So it's only for the first order differential equation, unfortunately. So what we do is that to plot the direction field in the solution curve of the differential equations, you consider a bunch of points and calculate the derivative. If the derivative is less than 0, you have the arrows pointing downward. If the derivative is greater than 0, you have the arrow pointing upward. you have the derivative equal to 0, then you have the horizontal line. Right? That way you can draw out the direction field. And from the direction field, you can follow the direction field to draw out some solution curves. In addition to that, so that is for non-autonomous first-order differential equations. In the case of autonomous differential equation, autonomous means that there's no explicit representations of independent variable in the equations. So in the case of autonomous differential equation, you use the concept or you use the technique of phase line analysis. Right? To actually plot out the phase line analysis, you need to find critical points, you need to find equilibrium solutions, and do the analysis that way.